Example number 10, the infinite plane of charge. So let's consider an infinitely large non-conducting plane in the xy plane with a thickness t. So there you have a picture of a conducting sheet, and you have to think that this is extending out to infinity in the x direction and along the y direction as well, both positive and negative. And the electric field vectors will be pointing perpendicular to the surface. But don't forget there's also electric field lines that point downwards as well. So there are charges distributed in the upper surface of this plane, but also on the lower surface of this plane sheet. So the electric field vector points in the positive z-axis and also in the negative z-axis. And a very important point to realize is that this electric field is a uniform field. These charges are all uniformly spread on this surface, which means the magnitude of the field is constant in magnitude and in direction. So our next step is to determine an appropriate Gaussian surface in which the magnitude of the electric field is constant over all portions of that surface. And then this is where I introduce something called the Gaussian Pillbox. And there you have it, the Gaussian Pillbox. This is really a small cylinder with a cross-sectional area A that is parallel to the plane of this sheet. This pillbox has three parts: the top end, the bottom end, and the curved section around it. And there you have the three sections. S1, the top end, where the electric field and the area vector are parallel to one another. The curved section S2, where the electric field is perpendicular to the area vector, and then the bottom end S3, where the electric field and the area vector are also parallel to one another. So let's now calculate the total flux of this Gaussian pillbox. Remember, the total flux of this Gaussian pillbox is the sum over that closed surface of the electric field E dot dA. And we're going to take the integral over all three of these surfaces, S1, S2, and S3. And out of these three surface integrals, you'll see that S2 surface, the electric field is perpendicular to the area vector, so there will be no field lines from E2 that are penetrating the surface. So this integral goes to 0. So we get E1 times A1 plus E2 times A2. But remember, the electric field remains constant everywhere, so E1 and E2 is really equal to just to E. And also the area of our cylinder on the top cap is the same as the area on the bottom cap, so we'll just call that area A. So in the end, you're going to get 2EA as the total flux from this Gaussian pillbox. Now applying Gauss's law, the total flux is equal to the Q enclosed divided by epsilon naught. And the total flux for this Gaussian surface turned out to be equal to 2 times E times A. But we also know that this charge is uniformly distributed. And so the surface charge density, sigma, is equal to the Q divided by the cross-sectional area A. So we can replace this Q with sigma times A. So let's put that into our expression over here. Q enclosed is the sigma times the cross-sectional area over epsilon naught. We'll see the areas will cancel out, and the magnitude of the electric field is equal to the charge density divided by 2 epsilon naught. But let's put this into a vector notation. And you would see that for the plane above positive z-axis here, we'll have a positive sigma over 2 epsilon naught. And when you're below this infinitely large conducting sheet, below the z-axis, you'll have a negative epsilon or sigma over 2 epsilon naught. And if you were to plot the electric field as a function of the position z, what would it look like? It looked like something like this. So along the negative z-axis, you have a constant negative sigma over 2 epsilon naught, and then as soon as you cross this plane, it quickly jumps up to positive sigma over 2 epsilon naught. So really, this whole jump is really sigma over epsilon naught. And this would represent the total change of the electric field along the z-axis. And once again, a very important assumption is it's very large. So this is infinite out this way, so that the electric field lines are all perpendicular to the surface. And this results in an electric field that is constant in magnitude and direction. Well, it's actually positive on the upper surface and negative on the lower surface. So it really doesn't matter where you're located, it'll always be the same amount. And we'll be using this result as we build a capacitor in the next chapter.